Hello everyone, my name is Akther. I am going to present mTeeth for detecting brushing teeth surface from wrist-worn inertial sensor. I would like to thank all of my co-authors for their contribution, my professors, NIH, NSF and Oral-B for supporting my work. Recent dental studies show that in a brushing episode, surprisingly more than 70% area of the teeth people do not clean properly. That's why most of the people wonder why they have toothache even though they brush their teeth regularly. Naturally, some question arises that need to be answered, such as do all of our teeth get enough brushing? Do we miss some teeth or overbrush some teeth frequently? So therefore, we need a system to characterize our brushing session. Several attempts are done with instrumented and smart toothbrushes, but they rely on user input and more than 80% people in the United States are still use manual toothbrushes. In this work, we focus on characterizing manual toothbrushing using wrist-worn inertial sensor. At first, we define the surface region. Since people brush group of teeth simultaneously, so we divide the whole teeth area into three broader categories and name each teeth surface by combination of three categories. As a result, we have 9 teeth surfaces. So the problem is, can we detect brushing teeth surfaces from wrist-worn inertial sensor? In our model, we use 3-axis accelerometer and gyroscope, which is included most of the activity tracker and smartwatches. The figure shown one brushing episode with annotation. To solve this problem, we face several challenges. We need fine-grained level data as shown in the figure and need tight time synchronization to avoid ambiguous labeling. Time series segmentation is also a major challenge since duration of surface varies a lot. Finally, we need to extract informative features from this noisy signal and between person variability is very high. To get the granular level data, we enriched a model dataset where videos are captured during brushing. Two independent coders are carefully annotated each surface transition from each video. In total, more than 10,000 levels are annotated. Now I present the pipeline of our model. Due to the time constraint, I will explain the main three components of this timeline. In our level data, we observe time spent on a brushing surface varies from a few milliseconds to several seconds. This poses a significant challenge to find an optimal window. If we choose our window size smaller, we might have insufficient amount of data to find the distinctive feature. If we choose our window size larger, it may create ambiguity and mismatch in labeling. Therefore, we seek dynamic length event-based approach for segmentation. During brushing, people generally perform either up and down or back and forth periodic motion with the brush, which reflect in the accelerometer signal as peak and valley, which as shown in the figure. We identify one valley, peak valley correspond to one brushing stroke. We identify one brushing stroke as the anchor event, which is efficiently detectable and prevent ambiguity. From each brushing stroke, we computed several features including accelerometer, gyroscope, and orientation feature. After that, we apply correlation-based feature extraction to extract most important feature. After extracting most important feature, we want to classify each brushing stroke to any of the 9 surfaces. Since inner surface brushing is completely different than outer surface brushing, we created layer-by-layer Bayesian network, where the first layer tries to identify the likelihood of inner versus out, where the second layer tries to identify the likelihood of central left light given the condition of first layer, and so on. Finally, model classifies the class with maximum likelihood. Furthermore, we also observe the stable pattern during the surface transition. That's why we updated the network by adding state transition. We perform the series of evaluation. First, we want to evaluate the accuracy of detecting brushing stroke. We see detection difference between actual count and estimated count is varied within 2 and mean absolute error is 4.2%, which is much better than acoustic-based method. Then we want to evaluate the between person generalizability. For that, we started with Lee-bound subject out cross validation, get a phonics score of 65%. For personalized model, we perform Lee-bound episode out cross validation to see the impact of within person variability, get a phonics score of 80%. We also perform tenfold cross-validation to compare with the recent work get a fun score of 86%. Up to now, I have presented the accuracy of 9 surface detection. But for oral health purposes, both user and dentist might be interested to know the total brushing duration on each surface. Recall the initial question, what we wanted to know from each brushing episode. Even though we applied Lee-Bourne subject or cross-validation, mean absolute error is less than 7.5%, so the agreement is more than 92%. In summary, it is the first work for detecting brushing stroke from wrist-worn inertial sensor, which create an opportunity to detect the correct way of brushing in future. Also, we present stroke-wise surface detection, but our video annotation did not differentiate between inner and swing surface. Also, we present tight time synchronization in the paper, which can be extended to other behavior. Interested researchers are welcome to check the method in the paper. Thank you.